Welcome to Shanti-Peace for mathematics. Many times it is required to obtain the Fourier expansion of the function in the range 0 to L, which is the half the period of the Fourier series. So whatever the function is outside in the range of 0 to L, we extend the function to cover in the interval minus L to L. So the new function will become even function or odd function. For example, what is the function is given you as this form. Let's say the function is this in the interval 0 to L. Now if you want to extend this function as an even function. So as you probably know that, what do you mean by even function? Even function means it is the symmetric about the y-axis. So if you want to extend this function as a symmetric about y-axis, then the periodic function in the interval 0 to L, this function is like this. So the similar image you will have here, and the same graph you will get in the interval L to 12. This is minus L to L, L to 12, and this is here it is 3L. So in this you will have the same type of periodic function you will get. So this is the expansion as a even function, I can say. If you want to expand your function as an odd function, and probably you know that what you mean by odd function as a graphically, that means it is a symmetric about origin. It means whatever the graph is on the first quadrant, the same graph you will have in the third quadrant. So in that case, your function is this in the first quadrant, the same function you will have it in the third quadrant, and you are extending your function as a periodic function in that manner. So this is known as a half range Fourier series. And so there are two types of half range Fourier series is there. The one of them is the sine Fourier series, another one is the cos Fourier series. So let's give the definition of both these Fourier series. The first one is the sine series, I can say. So it is also known as the half range sine series. Here your function f of x is given in the interval 0 to L. When we extend this function as a reflection with respect to origin, okay, that means we are extending our function as an odd function which is in the interval minus L to L, which can be described as f of x is equal to summation n running from 1 to infinity dn sine n pi x upon L, where this value of dn is 2 by L integration from 0 to L f of x sine n pi x upon L dx. And in the similar manner, the cosine series, or I can say cosine half range series, you required a function f of x which is defined over the interval 0 to L, and we are extending this function as a reflection of y-axis. So it is as an even function in the interval minus L to L. The Fourier series of this, which we can express as a0 by 2, the summation n running from 1 to infinity an cos n pi x upon L, where your a0 is 2 by L, 0 to L f of x dx, and an is 2 by L, 0 to L f of x cos n pi x upon L dx. So this way the half range Fourier series is defined. Still we don't know what is the uniform convergence of this half range Fourier series. So in the next I am going to discuss the uniform convergence of this half range Fourier series. So let us state what is the statement, that if f of x is expanded in a series of cosine in the form f of x is equal to a0 by 2 plus summation n running from 1 to infinity an cos nx. Then prove that a0 is 2 by pi 0 to pi f of x dx and an will be 2 by pi 0 to pi f of x cos nx dx. So in particular, this is in the previous case what we have, the function is defined over 0 to L, so your L is in that case it is pi. So that's why we have, this is the quantity we have. And this equality means it is a convergence, it is means the uniform convergence is there. So I need to say that it is uniformly convergent. And uniform convergence I already explained you in my one of the previous video. You may find out the link in the description as well as in the I button. You can find that. Let us try to prove this one. To prove this one, I have to integrate this whole quantity with respect to x in the interval 0 to pi. So just integrate this quantity, it's given to you. So that's why I am integrating both sides with respect to x in the interval 0 to pi. We will have, this is integration 0 to pi fx dx equal to a0 by 2 integration 0 to pi fx dx plus integration 0 to pi summation n running from 1 to infinity an cos nx dx is there. Now this integration and the summation I can interchange due to this uniform convergence. So that's why we can write down this is integration 0 to pi f of x dx is equal to a0 by 2 integration of the constant quantity that is 1 is x 0 to pi plus summation n running from 1 to infinity an is constant, so that's why it is integration 0 to pi cos nx dx is there. The integration of 0 to pi cos nx will be 0, that you can verify, and this quantity will have it is pi plus 0. So finally you will have a0 is equal to 2 by pi 0 to pi f of x dx. Here you just verify that this quantity is becomes 0 for any n belongs to that. You can verify yourself. The next quantity I have to prove that an is this. So for that I am multiplying both sides by cos mx with fixed n. N is fixed. I am multiplying both sides by cos mx and then integrating from 0 to pi. Then what we will get, let us see. It is integration from 0 to pi fx cos mx dx plus integration 0 to pi a0 by 2 cos mx dx plus summation n running from 1 to infinity integration 0 to pi an cos nx into cos mx dx. Now again, as I have talked in the previous things, this quantity will become 0. So that's why this quantity is 0, because a0 by 2 is constant. So this is a0 by 2 into 0 you will have, and here you can interchange the summation and the integration sign due to the uniform convergence, and hence we can write down this is 1 to infinity an is constant, the 0 to pi cos nx cos mx dx. And you just may verify that what is cos nx cos mx. The integration of this quantity will be 0 if n is not equal to m. It is pi by 2 if n equal to m. So that's why this is, when n is m, it is pi by 2. Otherwise it will be 0, as we have seen. That's why it is left is am into pi by 2. So finally you will have an, which is 2 by pi from integration 0 to pi f of x cos mx dx, and this is true for any m from 1 to infinity. So hence we have an is this, and we complete our proof of the theorem. I am giving you a proof of the next theorem by yourself, that you can prove yourself, that is stated in this manner. If f of x is expanded in a series of sine in the form f of x is equal to running from 1 to infinity dn sine x, prove that the dn equal to 2 by pi 0 to pi f of x sine nx. This I am giving you as a homework to prove yourself. Now let us solve some of the examples related to it. So the question is to find half range sine series of the function f of x is equal to x in the interval 0 to 2. Let us try to see what half this function is. First of all, extended is a sine function. We know that it is the interval is from 0 to 2, so that's why 0 to 2 is there, and f of x is x, so that's why the graph of this function is this. And you are extending this function as a sine series, so that's why it is an odd function. The odd functions are symmetric about the origin, so that's why the graph of this extension you will have this, and you will get the expansion of the Fourier series is actually the approximation of this function into the interval. So it is minus 2 to 2. And the half range Fourier series, that you know, it is defined as summation n running from 1 to infinity dn sine n pi x upon n. Here L is 2, because the question is to calculate the half range series. So that's why L is 2. The question was to calculate this only a Fourier series, then your 2L L will be 12 will be 2, and then your L is 1. So this is not the case here. Here you have to calculate the half range series, which is in the interval 0 to 12. So that's why your L is 2. Where your Bn is 2 by L 0 to L f of x sine n pi x upon n dx. So it is 2 by 2 0 to 2 fx is x sine n pi x by 2 dx. We are applying the integration by parts to solve this integration. So x as it is, the integration of sine will be minus cos n pi x by 2 upon n pi by 2. Then it is minus, the derivative of x will become 1. Integration of all this quantity will become minus sine n pi x by 2 upon n pi by 2 square. The limit is 0 to 2. When you put 2 here, you will have some quantity, and just writing this 2 by n pi as this, and this is the minus cos n pi left, because when I substitute 2 here, 2 will get cancelled. So cos n pi into this quantity is left, and this minus minus becomes plus. Here when I substitute n pi, it is sin n pi there. Sin n pi will become 0. So that's why this quantity will become 0. When I substitute 0, 0 into anything is 0, and sin 0 is 0. So only the quantity left is this. So finally you will have it is minus 4 minus 1 raised to n upon n pi. Hence the Fourier series of the half range Fourier series, you will have it is summation n running from 1 to infinity dn sine n pi x by 2. That's by summation n running from 1 to infinity. It is 4 minus of 4 minus 1 is to n upon n pi sine n pi x by 2. This is your required sine Fourier series. Let us solve one more example. Is calculating for the same function into the same interval the half range cosine series. Now first of all, since we are calculating the cosine series, the function we are extending as an even function. So in the interval 0 to 12, as we know, the graph of this function is this, and we are extending as an even function, so that's why it is symmetric about the y-axis. So the graph you will have it is this, and we are extending this function as this manner. So it is, we are approximating this triangular wave in this case, and we know that the Fourier series, sorry, half range Fourier series is defined like this: a0 by 2 plus summation n running from 1 to infinity an cos n pi x upon 2, because L is here is also 2. Now what is your a0? a0 is 2 by L, which is 2, 0 to 2 fx, which is x dx. So it is x square by 2. The limit is 0 to 2. It will be 4 by 2. So finally you will have 2. What will be now an? An is 2 by L, which is 2, 0 to 2 f of x cos n pi x by 2 dx. X is f of x is x, so that's why it is this. And applying the integration by parts, we have x into sine n pi x by 2 upon n pi by 2 minus 1 cos n pi x by 2 upon n pi by 2 square, and it is of minus sign. Limit is 0 to 2. When I substitute 2 here, you will have sin n pi here. You know that sin n pi is 0. So this quantity will become 0. Here you will have, when I substitute 2, you will have this quantity, which is minus minus become plus cos n pi upon n square pi square by 4. When I substitute 0 here, 0 into anything will become 0, and when I substitute 0 here, you will have one value here, and that is of minus, and this minus minus become plus, so it is minus 1 upon n square pi square by 4. This 4 by n square pi square is common out. The quantity left is minus 1 raised to n minus. So hence the half range Fourier series of x, we have a0 by 2. a0 we have calculated, it is 2, so it is 1 plus summation n running from 1 to infinity an. We have calculated an is this. So let us substitute that 4 upon n square pi square into minus 1 raised to n minus 1 cos n pi x by, that is your required half range Fourier series. Let us calculate one more example of this half range Fourier series. If fx is defined as x, it is interval 0 to pi by 2 and in the pi by 2 to pi. The question is to calculate the sine series, or I can say the half range sine series of this function. Your L is pi here because the interval is defined from 0 to pi. Let us try to see what is the graph of this. You just note that in the interval 0 to pi by 2, the graph of this function is x, so that's why it is this. And the pi by 2 to pi, the graph of the function is this. So you will have this graph, and you are extending this function as in sine series. So that's why its image is a reflection of this one with respect to origin. So whatever the image into the first quadrant, the same image you will have into the third quadrant. So the extension will be like this. So you will have the graph of this function like this as a periodic function. Okay. The extension extend your x-axis. So this is the graph of this function as a sine series. We are extending this function. So let's try to see what is the expansion of this function will have. So we know that the Fourier series, sine series of the expansion is written as 1 to infinity bn sine n pi x by L. L is pi, so that's why it is n x. So we have this is the things you have bn sine x, where bn calculate as 1 by pi, so 2 by pi integration 0 to pi fx sine nx dx. So it is 2 by pi integration 0 to pi by 2 f of x in the interval 0 to pi by 2 is x sine nx, and plus pi by 2 to pi it is 0 dx, because in the interval pi by 2 to pi the function defines as 0. So finally I am applying the integration of parts in this. So it is x cos nx upon n minus plus x sine nx upon n square. Limit is 0 to pi by 2. And substitute pi by 2 here, you will have cos n pi by 2. So you will have dn will be 2 by pi by 2 into cos n pi by 2 plus pi by 2 substitute here. This will become 1 because the derivative of x is 1. So that's why it is 1. Sine n pi by 2 means we cannot say it is 0, or neither cos n pi by 2 is 0. We cannot say that. And I substitute 0 here. 0 into anything is 0. And sine 0 is 0. So that's why we have 0. So we have bn in this. Finally, the Fourier series you will have it is, which is your function f, which is 1 to infinity 2 by pi in bracket pi by 2n cos n pi by 2 plus sine n pi by 2 into sine nx. So in this video we have defined the half range sine series and half range cosine series. We have talked about its convergence also, and we have solved a couple of examples based on that half range sine series and cosine series. Hope so you have understood what you mean by half range sine series and cosine series. You can solve some of the problems which are given in my lecture notes. So that's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in the comment box below. See you in next video. Till then,